Hey everybody, Mr. West here. This is a video specific for the building specifications for the FBDrone. There's a couple out there that want to know the exact dimensions, and so what I'm going to do is walk through on video and show you what those are. So get a piece of paper and a pencil and draw a plane and wing in a twin boom configuration like the FBDrone here, and then a fuselage underneath that where the nose sticks out some more than half of the fuselage length. So just to get general proportions, draw this kind of general picture, and then we'll apply the dimensions to it. Okay, so overall wingspan is two sections of the arm and wing. It ends up being 60 and 5/8, which is not really all that important. What's important is that it's two full sections of the 30-inch Dollar Tree foam board in here. Okay, so a total of 2 panels or 60 inches. And the reason why it's longer than that is because I have on the end 1/8 inch skin plywood skids on the ends that add some length, and the panels themselves are not exactly 30 inches. I've noticed they're 30 and an eighth sometimes, so this particular one happens to be a little bit bigger than that. Alright, so then you have a 30-inch wing section, and then it's a full 20-inch wide sheet that's been folded in half, basically. Using the arm and wing construction technique at EA or Experimental Airlines website, how to build the arm and wing. So build it as per his design. The only difference is that how I made the wing spars and position and stuff inside, that's quite a bit different, and we'll go into that a little bit later. But so for overall dimensions, 60 inches. And so what you see here is approximately 9 inches overall. You do lose a little. It ends up, if you do it completely and use the whole sheet, it's like 9 3/4 to the score on the inside, and you remove all of the paper on the top of the inside of the wing. So this dimension is 9 inches. A control surface of 1 3/4 here. Okay. Alright, so that's the wing itself, and so the tail section is 7 1/2 inches front to back, or back to front, and then overall length of the tail section is 25 inches in width. Let me move these things off here. Here we go. Okay. So the overall width of the tail section is 25 inches, and the overall width of this is actually 7 3/4. And this is a double Dollar Tree foam board. And the way that I did that is I just simply took 14 inches, actually about 16 inches of paper sheet by 25. And then here at the leading edge, I removed a 1/2 inch wide for folding. Just like you would fold the fuselage tube, you remove a 1/2 inch for the inside fold. And I completely just doubled it over. I hot glued entirely with spread hot glue, and do a perimeter hot glue here. And then just closed it up and pressed it. Take a piece of wood or something and press it on a nice flat surface till it all cools out nice. Now I have some angle here, and so all you do is you take this overall dimension here on the trailing edge is 25, and on the leading edge is 23, so it's a 2-inch difference. Take an inch off, cut a line, and that angle is there just for aesthetics. It could be square, it could be rounded, it doesn't really matter. Okay, now then for the verticals, so then the total height of, and there's an angle here, the total height is 9 3/4. The leading edge height is 8 3/4 at this point right here. So 9 3/4, 8 3/4, and we're just counting right here. We're not counting the control surface. So this is 3.5 inches here on top. 9 3/4, 8 3/4, 3.5 inches here. All right, and then the overall base width is 7 inches. Okay, 7 inches here. 9 3/4, 8 3/4, 3.5, and that'll give you these angles. Just plot this on a piece of material that is 9 3/4 by 7, and then you can plot that out real easy. And then the control surface is 2 inches. Follow that same angle right there if you wanted to. And I take off about a quarter of an inch here off the bottom. It's not necessary to do that. If you wanted to, you don't have to. Okay, so then in the between, so I've double folded this control surface here, the horizontal stab, and then I just notched out. So the spacing between is 14 inches on center. So these booms are 14 inches on center to each other, 7 inches from the center line, obviously. 7 inches to center line, and that's where the vertical stabs are. They're right over the top of that. And then the elevator surface in between, I'm leaving a little bit of space here. There's about 3/8 of an inch here, 3/8 on this side. So the overall control surface is 13 inches by 2 inches this direction. 13 inches by 2. These are on 14 inch on center. And that takes care of the tail section. Alright, so let's flip the bird, flip the wing over. So the control surfaces on the wing are 22.5 by the 1 3/4 that I mentioned earlier. 22.5, 1 3/4. The boom locations are again 14 inches on center. So this wing has within it, and I used the 3/8 dowel. I used actually I used a 1/2 inch dowel inside here. So there's 2 of them. There's the main spar, which is on 1/3 position. So if you take 9, divide that by 3, that's 3 inches in. So at 6 inches in, and then this back dowel is at 3 inches as well. So I divided this into thirds. 3 inches from the leading edge, roughly, is a spar. And so actually, back up a second. So when you're building the wing, you measure from the back edge. It's much easier because this is a fold, right? So measuring from the back end, we have a 3 inch and then a 6 inch is the location of that those wood spars, those dowels. Any spar could be used. I happen to use wood dowel, and I had to rummage through the dowel bins to find the truest, straightest ones I could find. And I went through 20 or 30 of them, and it was difficult. And another thing too about spars, let me check on the video battery, make sure. Another thing about wood dowel spars, or even square, is whoops. Don't knock the camera over. Stand by. We're experiencing technical difficulties. Let's go back to the middle there. There we go. The thing about any wood, any raw wood is going to absorb moisture. So if you're high moisture environment, what I would do is I would take those dowels and then I would coat them with, first I would spray them with a clear lacquer, not water-based, but a clear lacquer spray to try to seal them up. And it's going to take about 2 or 3 coats and sanding in between, and that'll prevent, or help prevent, I should say, moisture attraction into the dowel, and then you get warpage, right? So when you store your birds out in the garage, and maybe the garage gets hot or it gets real cold in the winter, the wood's going to want to maybe warp because it's attracting, it's pulling in moisture. Seal them up first. That's a good idea. I haven't done that much. I'm in a real dry environment here in Southern California, so I don't have to worry too much about moisture and all that. Okay, so then the dowels are located here and there, and the reason I'm saying that is because what I do is I've tied, and this is a little bit on the crude side, I've wire tied down and around the spar with, it's called safety tie wire, and the military uses it to tie nuts onto bolts. So they drill through it and they wire tie it and they twist it, and that's called safety wire. That means, so instead of a locking nut that we trust, you know, when we're not flying, right? We're not an aircraft. In the military, they use locking nuts and they wire tie them so they don't come off and then be ingested into the engine. Some critical location, like all engine components, anything to do with the engine in the nacelle has wire tied safety going on in there. So this is the same idea. I've taken a wire that is twistable, malleable, but yet it's pretty strong. And I go down and around the spar, and I come back up, I loop over, and I go back down and around, and I just twist tie it. And I've done that in both locations here. So this is actually not hot glued in. Actually, it is hot glued tacked in here at the back edge. The front end is just completely wire tied. And I put on the bottom of the finished wing, I put on a plate, a pressure plate here. And what that does is distribute the pressure that the booms apply from you know, your pitch moments. And because this is just foam board, there isn't any structure underneath here. The only thing it is your spars. So you really want to make your spars down to the bottom of the wing. And if you're going to do the booms like this, you can tie them like so. You could also just hot glue this on there. That will work too. But somehow you need to kind of join those two together. You could take a couple of small screws and go down into the spar, though I don't recommend that because you're screwing into the spar, which is sort of counterproductive. There weakens it. All right, so tip skids. They're basically just a wedgy shape. If we turn this upside right, that's a kind of a wedgy shape. It's about 3 inches. It can be a lot less. It could be 2, 1.5 inches, something like that. But the reason that they're there is because this is a single, a tandem style landing gear set, and so the tips will drag on the ground, and the tip skids there, and they're plywood, and they're just designed there to take up that pressure. Okay, so let's get into the rest of the dimensions here. And those dimensions I'm referring to are the length of, so from, what we'll do is we'll measure from leading edge to leading edge. Okay, I've got 24 inches from the leading edge of the wing to the leading edge of the horizontal stabilizer. Okay, and then I have my booms reach to the spar. Very important that it reaches to the spar. Does it need to go to the front? No. It just needs to go to the spar, just past it. That way you can tie it or fix to however you're going to fix the boom to it. This could be wood, it could be carbon fiber arrow shafts. These are aluminum, which are a little too flexible for the weight of this tail section. So I had to reinforce it with some the expensive foam board that you get at Office Depot or someplace like that that has foam board, not the cheap stuff. And it's quite rigid. So I made this wedge, essentially a tapered. It's narrow here and thicker at the end. This acts a little bit as a tail skid as well. And I just hot glued that on the length of. So I did the assembly and everything first, and then I put this on later. And this, of course, is all taped off. And I pre-taped all that first, and then I hot glued it to the arrow shaft. And it took all of the up-down wag, the pitch wag out of it, made it a lot more stable. Okay, so I'm thinking that's just about it for the wing and tail section. So we've got that. We've got the span width. The overall length of these booms are 28.5. And I've taken the boom all the way to the trailing edge. Is that necessary? No, it could stop about two-thirds in. give or take. Just the critical number for proportion and arrangement is that this is 24 inches from that leading edge to this leading edge. Okay? Enough about the fuselage. Let's set this aside. And this is very lightweight. This is maybe a pound and a half, something like that. So let's get the fuselage up here. So I'm just showing the overall dimensions, and then what I'll do is I'll show the actual construction technique. Okay, notice the angle. Okay, anytime that you mount the motor above the wing, the pitch moment, so the pitch moment is down here. So this is where the plane pitches. All right. So anytime the motor is above the pitch moment, you must change the angle of the motor to point to at or about in front of the leading edge of the wing. So some distance, like 1 to 2 inches is my rule of some angle. So if you took this line and you just extrapolated it forward, it'll end up over here, this pointing the motor down towards the fuselage when it's above. And what that does is it compensates for thrust angles. So when the motor is up here above and it pushes the nose down, right? But when it's on an angle like this, it compensates by pushing below the nose and keeps it on a level flight. So when you power up hard, and this is straight up and down, it's 90 and it's some 4 inches above the pitch moment, then it will want to pitch the nose over. Make sense? Likewise, if the motor were down here and pushing parallel to the pitch moment, then it will push the nose up. Make sense? Okay, so that's the other, and then the other thing too is like on typical motors that have, or typical airframes that have a motor in the front, they always have the motor pointing off to the right a little bit and down. And the reason for that is for torque roll. It wants to go to the opposite. So the prop is swinging in a clockwise and the plane wants to go counterclockwise. So in the back here, it's not so much an issue, but if you have a real big torquey model, if you have a real torquey engine, motor rather, then it will want to make the plane roll to the left. Therefore, you want to point the the motor angle towards the left side of the plane, which will cause it to turn right, which counters the torque roll left. Okay, anyway, so notice that there's some angle here, and that some angle is approximately 5 degrees. So you basically build the fuselage, take it to the chop saw, and it's best that you have a chop saw that you can dial in the degrees. Place it down onto the table, chop it at 5 degrees, and then this just simply gets hot glued on here. Now this plywood material right here is found in the Home Depot plywood handy panel section. It's like a 2-foot by 3-foot panel, and it's real lightweight. It's an import plywood, and it works really good for this. It's fairly stable. Some of the pieces in there are going to be kind of warped, but this works really, really well for me. Okay, so the dimensions. So this FB is started out at 24 inches, roughly. So build yourself a 24-inch fuse section. And the reason for this width is to allow 2 batteries to lay on the bottom here in the battery bay, to lay side by side with some slight friction. So the inside dimension is the exact width of 2 batteries laying side by side. I built the fuse around those 2 batteries. Then they just slide fore and aft to adjust for the CG. Okay, so that's the reasoning for this width. And the other is that I wanted to reduce the height here. So wind, a side profile, when wind is blowing at a crosswind to you, this will have less negative effect on the plane. The wind will have less influence on the plane with a lower profile on side. And it's rounded as well, so that also helps. So the dimensions here for this tube on the outside is 4 1/8 by 2 3/8. And those numbers really are irrelevant. You can make it big enough to hold your batteries, and that's all that's necessary. It can be, you know, whatever. It could be square if you wanted to. Alright, so on the bottom, I have these inline wheels, which to me is perfect. I mean, it's really low profile. I don't have any metal gear hanging off of here. That's also additional drag and additional weight. And then with having aluminum gear hanging off here, this would have to be reinforced and adds additional weight, because that landing gear would easily rip out of this foam board fuse. So that it just brought in more, and then you'd have to have a steering nose wheel, and then that takes reinforcement and another servo. It just all added up to additional weight. This thing steers on the ground for landing purposes only by just using aileron to rock back and forth. So imagine you're inline skates and you're skating. You just lean left and you go left. Lean right, you go right. Inline skates work just like that. So this is a simple plywood base that's hot glued. It's got a cutout for the wheel to fit in here, which is a bit oversized. Could be a smaller hole, but ventilation is nice too. So, and I use a metal axle that runs across. I hot glued it in place with a wheel in it, and then I used some wood material here, like 3/16 by 3/16 square, to brace on either side of the axle. And then I used them as stops for centering the wheel. I just came up to short of the wheel there on both sides, and it doesn't cause too much friction there, and it keeps the wheel in the center. Did the same thing with the front end. This is an aluminum arrow shaft that runs across, and these are cut, and you can use this. You can use your utility knife to lay it flat on the table, and you roll the knife around the circumference of the arrow shaft, and you just keep rolling, and it ends up scoring it. And a lot of times with the bigger pieces like this, you can just snap and it breaks off. It'll be real sharp, so you need to finish that off nicely. I've got the speed controller out here in the slipstream on the side. It comes around to the back end, and the motor is not mounted here obviously, but the motor connects there. This is my video battery that I permanently installed back here, based upon the CG and everything. It made my batteries, with this being here, it made my batteries sit right in the middle of this zone for moving back and forth. Okay, so enough about that, I think. Let me check the video battery. And we're just about down to the bottom. Alright, so what I'm going to do is we'll call it good right there, and then I'm going to put together then the techniques of how to make the fuse and talk a little bit about that. Actually, you know what? I might be able to fit it in. Hold on. Okay. So this is what the wing looks like in this wing that I have on the phone, on the FBDrone. Is that I have, instead of the plywood, or not plywood, this is actually solid wood right here, and it's a thin 1/8 inch rip, 3/4 of an inch tall, and this is poplar. You can use maple, and it was continuous. It was 60 inches. Lined up on edge like this creates an I-beam. It's extremely stiff. Better than round, better than square dowel any day. Even better than carbon fiber arrow shafts, in my opinion, or even aluminum arrow shafts, which are still way too flexy. I mean, you can use them, but if you're using a real light airframe and everything, this is like 4.5 pounds total. So it needs something that's pretty rigid. That wing needs to be rigid, and the more that rigid it is, the better for flight performance and so forth. Takes a little flexing, right? That's okay, but not, you know, bending. Because what you end up doing is kinking the surface on the top and anyway, under wing load. Okay, so this is a typical I-beam. And my point in this, in showing you this sample that I made, which is an Orman, the cord is 8 1/4 with 2-inch control surface. It's about 15%, meaning you take the cord and the height and you get a percentage of, so the height is 15% of the cord. The thickness is 1 1/4 overall, and this section is 6 inches long, and it weighs 31 grams of this section, and there is a clear film on this surface here all the way around. 31 gram per this 6-inch section, 8 1/4, 9, 10 1/4 total. Now this wing cord is a little small for this plane and this load, in my opinion, so I went with the full sheet. So in other words, it was 9 3/4 to here, about 9 3/4 back. Technique right here is that you're sanding flat the bottom sheet. So you take the paper off 1 inch off the bottom on the inside, and then you take a sanding block and you sand it down to near 0. You leave just a tiny bit of the bottom paper. Don't disturb the bottom paper when you do the sanding. And that way the two come together to create only one thickness right here. If you bring two sheets together, it has two thicknesses, right? Then you have this draggy. You can do that, it's okay, but this actually makes a mating surface here that's parallel to this surface, so it glues together really well. Okay, so follow the Armin instructions at EA. It's taking the paper off of the inside top all the way to the back. From here, you leave the paper on the bottom on the inside. Then you make these locations. This is 2/3 of the wing right on the center of that spar. Make these 1 inch. These could be 3/4 inch. They could be 1/2 inch, but it kind of stiffens up this bottom area at 1 inch wide, which is real nice. Hot glue those down as locators. Hot glue then down your spar, and then this other locator, just butt right up to it, hot glued. Now this piece on top is 2 inches wide, this doubler on the inside. I peel the paper off of the inside of it so that it will curve down and disperse this to give a nice radius curve right here. You want this continuous curve. You don't want kink, 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 you know, these bends. So in general, you want this to be one continuous flow all the way around. And in the front, I use the Dollar Tree bamboo skewers as a leading edge reinforcement. So I just hot glue them. They only come about 10 or 12 inches in length. So you just hot glue them down and overlap the pointed ends like so with hot glue, and then butt the square ends together as you go. And it's just simply like an impact, a leading edge impact. It'll reinforce it, and it won't go in so far. Okay, so this one has the dowel in it. It doesn't matter what you use for a spar per se, but it needs to be strong enough to carry 5 pounds of wing loading. So that's what it should look like, minus the control surface. Use the full 10 inch. So this is the full width of a 20-inch panel or sheet, right? That's the idea. And then, so you're just making a sample right now too, guys. Practice, make samples like this. You can substitute your wing spar material with like pink foam, or you can use this white, the white foam board as a spar in here, just to get these dimensions and play with folding and hot gluing and putting all this substructure inside. So while this is open, you lay out all these pieces, locate the top one while it's laid out flat, hot glue it down, and then fold it over. And all you're doing is applying a little bit of hot glue on the top of the spar there, making contact. Let that get cold, and then this is still open here in the back, right? And then you run a bead across the back, and then you take a long flat pressing board or something that you can press this down with continuously, and then you close that back end up.